Okay, it looks like it's working. Uh, so today I just wanted to give a brief presentation and introduce you a simulation tool that I've been working on really mainly on in the weekends as a weekend project in the past few months. So hopefully useful for IMNS and rest of the Triple E, both staff and students. Maybe help them in either teaching or the research or the other projects that they have. So I want a bit. Uh, sorry, was working. Yeah. So I want a bit backtrack, go a bit to the past. Around I think it was summer of '97 or '98 that I bought my first few CDs. So these are actually the pictures of the CDs that I scanned back then many years ago. So obviously, Plays Come First. That was year of Flight Simulator '98, and Visual Studio '98 for coding. Anyone who did a piece of coding on Windows at the time, that was the main software tool. But I also bought this CD along, which was a bit curious on PC electronics, what's included inside. For the eagle-eyed audience, they noticed it's actually earlier than '98. That there was no Windows 98 at that point. It's compatible with Windows NT and Windows 95. So actually, what was in this CD? It was a bit mishmash of various software. So the olden days, there were a lot of software. So you can see there were software for teaching. You can see there were software for PCB design pads, which is now part of Mentor Graphics. And you could run these. Some of them were just informative. Some of them were simulation. Some of them were design. So I just wanted to give you a feel of what was the landscape many years ago in electronic and how we progressed. So I will give you actually a quick demo of one of these softwares. It's not in the CD, but I will explain now. So it was called EWB, Electronic Workbench, and it was written for MS-DOS. So the version which I'm showing you now was written in '91. This was quite a long time ago. And later evolved into Multisim from National Instrument. It still exists today, and you can download it. It became the most popular EDA back in 1999, and it really has a long journey. So the one which I'm showing you, I got it by a floppy disk probably in '96, '97. It went to various CDs, then DVDs, then multiple HDs, SSDs, and it finally rested in the cloud across the almost 25-year journey. So the one which I'm showing you is using I put it on my screen right now. So it's running an emulation on DOS. So that DOS also is running inside the browser. So it's a kind of multiple level of technology, which I a bit explain later. So you can see that the DOS actually run, and it's Electronic Workbench, which was by Interactive Imagination, Image Technologies back in Ontario. Then was later bought and merged into Multisim. So as I go into this, it's quite familiar. Nothing has changed much. You have multiple bits and pieces, function generators here that can set values, oscilloscope, body plot analyzer, and actually I can run this, and it runs. It's just showing an RLC circuit with a bit of oscillations. So I can actually change things, and live is changing the parameters. It's doing the body plot. I can move my cursor around up and down, and funny enough, it's actually running in the browser as a full system. So you can actually forgot how to work with these, but yeah, you can connect your circuit, open. Let's load another file. It has, for example, the circuit, say proceed, so another circuit, and then you can run that circuit. So kind of nothing has changed very much from the past. We have similar software again. Okay, let's go back to the slides. Right. So let's a bit of background on how it started. So it started with SPICE, which is simulation program for integrated circuits. So SPICE, mainly people these days use it for actually discrete components, but it was actually designed with integrated circuits in mind. It was first released in 1972 by Berkeley as a teaching tool. It came from earlier than 1972, but in various projects which were closed source, but then it was open source at Berkeley. It was published later on the BSD license, which is an open source license, and it carried on until 1991 as SPICE 3F5. That's a version number of it. There are a lot of versions which they got expanded from the original version. You have made here PSpice, which was the basis of ORCAD, still somehow exists until today. HSpice is a professional enterprise grade. It's by Synopsys now, and it exists as one of the top simulation tools. LTSpice, you're probably familiar with it. It started from various things, ended up in linear technology, and it is free now, but it's not open source. The open source version that it continued is now called NGSpice, that has been updating. Last updates were in a few days, weeks ago. There were more emphasis on a graphical user interface because graphics of the computers of those days were getting better and better. It was, as you saw, it was much more convenient back in even 1991, the demo which I showed you. It was convenient to use a graphical user interface rather than coding things in with original SPICE programs. And there was more push toward the schematic entry. What happened since? User interface and user experience, so UX as user experience and user interface, hasn't really progressed much. Actually, probably has worsened. So there is really not much user experience difference from what I showed you in the design in 91, and majority of the software, even the commercial grades that you are using today, it's similar or probably worse. So majority of the industry, from all those little softwares, it went into more consolidation, and larger enterprises kept growing from those simulation tools that it existed. And especially after year around 2000 and 2001-2, with the introduction of Java and Java version 2 Enterprise Edition, which was maybe called J2EE, a lot of enterprises and moved to the idea of integrated development environment, IDE, and Java was a good solution for this. So it's as a legacy, this exists. So a lot of software that you see, MATLAB, COMSOL, Cadence, it is all based on this notion of the Java Enterprise IDE. It's good for the enterprise which are not focused on they're not software people, but they're making the software for a specific industry, but obviously it doesn't give really a good user experience for the end user. Another problem that it exists is everything is proprietary, and unfortunately the software don't talk with each other as well, in the sense that the format that it is closed, so the format that it is the data is saved is actually closed, and you cannot share it within different software. Sorry. And actually, if you want to share it with someone else, so if you want to share your design or circuit with another university, another non-profit, you can't. It's tightly controlled, and you have to sign some legal documents and license agreements for this to happen on a case-by-case basis. And for exactly the same reason, no chip publication, no circuit publication is really repeatable, because you can't have that access to the raw code to repeat it yourself. So either the PDK or either the circuit itself would be under various licenses. So you cannot actually include that or open source it or put it somewhere that anyone else can repeat it directly. So this really raises the question that are we doing science here in our publications or not, because it's not repeatable. So what's happening today? So there are some new changes happened very recently that for the first time ever since the invention of the IC by Robert Noyce and the Fairchild Semiconductor, there is an open source, fully functional open source process development kit that you can design a chip in. So some people in SkyWater and other companies which I mentioned, they decided to open source, buy this basically slightly older node technology and open source it under open source licenses. So it's fully public, all the information is out, and you can use it without signing any legal documentation. And Google and eFabless, so everyone knows Google. eFabless is a company which takes some design and basically aggregates it similar to an MPW company, a broker, and then you can fabricate the chips. And they have been offering free chip fabrication under the condition that you upload your design as an open source and make it public. So if you make that, you enter a competition and they choose per run 40. So they have already, the first run has happened. They have selected 40 designs, and it's going to keep going on at least for the next few rounds. And it's totally free. So something which usually costs 10 to 15,000 euros, it's going to happen for free under the condition of open source. But potentially cannot use commercial software because of those sharing license agreements. So if you design something and put it open source, this might be used for commercial reasons or by someone in another company, and that would be straightforward breaking the license agreement. So it's not possible to use commercial software really in this context, or existing software. So there are open source software exist from long time ago and from recently as well. But obviously the majority of focus is on digital implementation. So for example, Open Road Foundation has a software which converts RTL directly to GDS. And the majority of the submissions which happened on these rounds are in that digital implementations. But what transistor level simulation? So we are always interested in mixed signal, analog design, and transistor level. Even for digital, for high speed or low power, we need transistor level simulation. So what about that? So that's my contribution. So I introduce eSIM here. So this is the user interface, as I explained very briefly here, and then I will show you. Then you can run the software yourself. The input is netlist, so you give a SPICE compatible netlist to it, and it will plot the data for you, and it provides you detailed information that you have entered into netlist and what's happening to your circuit. And you can directly download the data, the raw data, as a CSV file if you want to process it in MATLAB, Python, or Excel, or any other software that you have. So you can try it right now. Please go to esim.dev on any browser that you have, and actually you can it runs. You can click run and see what happens. So hopefully you will be still listening, but I will continue on the advantages while you're playing with the software. So what are the advantages? The main thing is netlist based, is text based. Why not schematic based? It's easily version controlled. So like any other piece of code which is text based, it can be version controlled, and that has a very huge advantage in documentation and progression of a design. It's searchable, it's comparable, it is easily shareable, it's text, so everyone can read it, everyone can understand it, whether a human or machine can easily read it. It's descriptive, unambiguous, you can annotate it very easily, you cannot annotate a schematic very easily, you can comment and annotate. You can script it. It's very good for automation because if you have a scripting software, you have an automation software, you can easily generate those netlists and help you in either optimization or scripting of other procedures that you have. Other advantage is runs in the browser. So actually it computes in the browser. There's no server involved other than you downloading it into your local PC. It's multi-platform, it's agnostic where it is running. It runs on phone, it runs on your PC. It's not designed to work with small screens, but it can run. There's no installation. It works offline as well. I haven't made it to work offline as a PWA, but that's easy transformation. Its goal is not to design a chip with it, at least at the moment. Okay, so please do not compare it with a large enterprise software. It's for rapid brainstorming and sharing of circuit ideas. If you want to send the circuit idea that you have to your colleague in the other university, then it's super easy to do it. If you want to put your circuit idea online and want people to test it and from other disciplines to test and see how your idea works, then you can do it very quickly. It respects the user privacy. There is no data uploaded. Everything remains on your PC and remains private. So if you have a circuit which is patentable, you can still do that. Open source under MIT license. So I will give you a quick demo as well because time is running out. I have to be shorter on slides. Okay, hopefully you can see this. There is a transient simulation here, and as you can see, it plots. You can plot different colors, and you can enable, disable the signal. So you can disable everything, enable only this signal. This works quite fast. So there's a GPU accelerated plotting over here, and you can plot quite long sequences here. I don't want to go too long. But you can increase your resolution here, and it will quickly plot the data. You can zoom in and move around. You can try a DC sweep. So this DC sweep is just doing an IV curve, just plot the current. And again, you can go, for example, higher resolution here. Sorry, it's plotted again everything. And some extra features that you can put to access. Some extra features added, and it's always developing. For example, you have a slider now that we can actually work out which one of these sweeps that you are putting here they are actually seeing plotting. It's constantly, I add extra features as there's time. Okay, so if we go back to the slides. Explain the advantages. So how it is built, I super quickly go through this. So it has really two main development branches, and especially runs on a simulation backend. Put my pointer. So it runs on simulation backend, and then it has basically a user interface front end. It has directly 27 dependencies, and total has around 686 dependent code. The simulation backend is ngSpice, which I explained earlier, is an open source code which has been running for a really long while after the original Spice from Berkeley, and it's using the latest version, 2021 version. It's fully Spice compatible, and it supports the latest version of BSIM. For those of you who do transistor level simulations, you're familiar with this. It's running BSIM 4.8. I have already included predictive technology models from Arizona State University. You can visit their website. So these are co-developed with ARM Technologies in Texas. And from 113 nanometer to 16 nanometer, I've included. You can choose a transistor, mix and match between them. And the innovation comes really on the simulation backend. So it's run on a piece of toolchain called Emscripten. So it's a C++ compiler toolchain. It compiles the C code into WebAssembly, and then it runs that WebAssembly. It's designed by some very smart engineers at Google, and the Google JavaScript engine, the V8 team, that developed as open source backend. And it runs on WebAssembly. So it's basically, this is very new technology from 2017. It's assembly for the web, and it is now a standard. And since 2017, it runs in all the browsers. It's literally something that's very similar to actually assembly coding. We have some some problem on the doesn't run. Okay. Some user interface, which I just briefly go through this, the plotting, which actually I've made that myself. So the buttons and bits and pieces, it's mainly designed in React, which is developed and maintained by Facebook. It's running on a JavaScript TypeScript engine, and everything at the end bundles up into one piece of code, which again can run into major browsers, and is hosted on Vercel, which is a content delivery network. So the advantage of that is cached on remote server globally, so everyone has low latency access to the download. So conclusions, it decouples the simulation engine from the user interface. That both of these can be developed separately. There is no necessity for integrated environment. They can add two software as long as they're open source. They can talk with each other. It uses the latest modern user experience and user interface. It uses the same existing standards and ecosystem which are available for all other softwares that you are daily using, and improves the long-term maintenance of the code, which is very important for open source project. And no scaling costs, because it's running on the browser. There's no server cost for this. Millions of users can read it simultaneously. Future works, parametric sweeps is something that I'm working on, so you can parameterize everything, widths and lengths and everything else, to get Monte Carlo and parametric sweeps. I'm going to add the Skywater model, so actually then you can use it for making chips. And what is lacking at the moment is Verilog A models and the BSIM CMG for FinFET. So under 16 nanometer, so 14 nanometer to 7 nanometer, and below you cannot run at the moment, because those models are based on Verilog A, which is not supported in ngSpice yet. So that's the next big challenge. Okay, thank you for your attention, and I'm open to the questions.